Good afternoon. So I'm Gary, and tea is in 10 minutes. So I'm going to talk about cloudy without apology. I want to tell you I'm a horse. This is something really different. I'm not a nighttime gamma ray or X-ray astronomer. I'm a spectroscopist. I'm an unashamed spectroscopist. What really gives me joy is to look very, very carefully at the light that has come to us across the cosmos, individual photons that interacted with matter perhaps 10 billion years ago, came across the cosmos detected by our photons, those photons detected by our telescopes, and they got a message they want to tell us. They're screaming at the top of their little tiny voices. They're telling us something. I want to read, I want to listen to what they're saying. I want to hear that song they want to sing. And so Cloudy was a code I started working on back when I was on the staff here. The code is, after controversy between some postdocs with Willie Fowler and Fred Hoyle, the code is named after the local weather. But that is, the idea was to build the perfect instrument that would be able to tell us what kind of light would come out of anything. And so these are going to be just some examples. They're actually objects I've worked on. This is the nearest star-forming region, the Orion Nebula. And here's Eta Car. That's a highly magnetized, very massive star that's going to be exploding very soon. We're very fortunate that the field is not pointed at us. It would be an extinction event if it were. This is the Crab Nebula. This is a project done with Andy Fabian. It does relate to cool core clusters. In the case of the Crab Nebula, we can actually look very carefully at what's going on. We know exactly when this was created, when it exploded. If you look at the imaging, the spectroscopic imaging on the left, if you look in the middle panels are high ionization species, and there's a highly ionized core, a halo, around the molecular core. The upper left-hand panel shows molecular hydrogen emission. It also formed dust. And so this bad boy was able to create molecules, a rich inventory of molecules, and also create dust in an astonishingly short time. This is trying to tell us, screaming at the top of its voice, big voice, how to make molecules and grains really, really fast. And that has implications for what JVST is seeing in the high redshift universe. This is what Martin actually hired me to work on, the radio galaxies. Martin Longear had a generous allotment of IUE time. IUE was launched in 1978, was looking at the UV spectrum for the very, very first time. So the goal here is that these photons have come to us. Now, I'm not talking about standard issue that we know exactly what this is, put it on a BPT diagram, let's go home. I'm talking about exploring. You're looking at something that you don't know what it is, and you're going to use the spectrum to tell you what's going on out there. The spectrum can tell you things about composition, density, or temperature. And so the challenge then, here on the Earth, we're stuck here on the Earth, we're observers, is tantalizing. We can see, but we cannot touch. And so we can see these objects, we can't touch them, but their photons touched us. What can we figure out from that? There's an old saying, I don't know where I was told this, but I took it to heart, that when you launch a career in astronomy, you should have two types of projects. You should have the quick project that's going to get you a job and get you a grant. These are projects you do, though I was always told when I was here in the 70s, if you do 6 papers a year, no harm will come to you. Most recently, what I heard, if you do your 25 papers a year, no harm will come to you. There are those projects, but then there's the big project. And if you told anybody you were going to do the big project, that you wouldn't get a job. And so if I told anybody I'm going to write this code, it's going to be done in 20 years, I'll see you, that would not have worked out. But it was a wonderful time because I had the office right next door to Martin, and Martin knows everything about everything. And so you just go there, and it was like Wikipedia with a smile. And it was a wonderful experience. Alan Burgess was down in Dampt. And Mike Seaton, the fellow who invented this field, was down at UCL, which was where IUE was controlled. And so the goal here with our discussions with Martin is what are the thermodynamic limits that a gas would go to in all extremes? So if you go to very, very high densities, collisions dominate, that's called LTE. If you go to very, very high radiation density, so this plot has density going up and down, and so it goes from IgM densities up to almost the Earth's atmosphere. Then across the bottom is the intensity of a radiation field. On the left is a very faint radiation field. On the right is very strong. The right is strict thermodynamic equilibrium. That's what is where radiation is so strong it will establish thermodynamic equilibrium all by itself. So that would be the interior of a star or the universe before recombination. And then there's all kinds of things happening in the middle, and then you can place different astronomical objects there. So if you go to all these extremes, then the middle is covered automatically. Another way of thinking of this is that a hydrogen atom actually has a very boring life. It only knows how to do three things. And if you do them exactly right, following the quantum mechanics, then that hydrogen atom you're thinking about could be the center of a sun, it could be at one Schwarzschild radius, it could be inside a radio jet, it could be inside the molecular torus around an AGN. So the idea was to fully capture the microphysics without compromise. And then the snarky comment, if you take care of the microphysics, the macrophysics will take care of itself. So it was a long slog. Last year, Nature introduced a new series of articles which they call Codes of Honor. And they're talking about an idea that it was in the US decadal survey last time, and that's the idea that there are large software projects which by themselves are not highly publication intensive, but which form a greater value. And so what Nature was going to do is highlight these codes which contribute to the community and which represent a great deal of work. They suggested that the practitioners who we call software architects. So this is this tension between facility creators versus facility users. And so this is something that was in the decadal survey, and the idea of the facility creators, it's a great deal of work, and they shouldn't have the same citation count H-index matrices to determine success. So what they said was Cloudy was the first open source, broadly applicable code. So this is from the ancient times in the bottom up to the top. A very few seconds about the ancient times here at Cambridge. So this is the mighty supercomputer I had access to, 3081. It was the top 3 computers in the UK. It had 2 megabytes of memory. So all of Cambridge University shared 2 megabytes of memory, but that not to worry, because one job could not have more than 64K. The operating system was a thesis project called Phoenix, because it arose from the ashes of OS 360. It crashed every 90 minutes. You picked up really good habits about sharing your work. So this is what Aristotle would call an accidental difficulty. In a problem, there's accidental and essential difficulties. So the essential difficulty is this in dealing with light. If you talk about gravity, and we've seen a lot of simulations of gravity, the force you're looking at is here. The equations you're dealing with light are the many-body Schrödinger equation in the middle, and at the bottom, the equation of radiative transfer. That's the essential difficulty that we have to solve. And if you get to something like iron, you're talking about the many-body Schrödinger equation with 26 bodies. And you want to solve that to very, very high precision. And so there are a number of codes. The premier ones were developed by Mike Seaton at UCL and Phil Burke at Queen's University Belfast, and they're still doing much of the heavy lifting. Now, you talk to somebody that I'm doing, what I really like to do is think about the spectrum. The answer should be, probably most of you are now thinking it, well, gosh, We've known about Coulomb's law for a long time. That doesn't sound very interesting. Well, that's perhaps is true for the very strongest lines. Perhaps the lines in the BPT diagram are known for sure. But if you get anywhere near the research, there's surprisingly little known. And so very faint lines are generally going to be from highly excited levels, and they're very poorly treated to go up to highly excited levels. There are an infinite number of excited levels in an ion at zero density. So computers are not very good at dealing with an infinite number of levels. The real critical problem here is this I think the answer is none, earlier mid-career atomic physicists who know how to work on this field. So the solvers are easy. The part that cloudy is work that does itself are fairly easy. I don't want to say it's too easy, but the solvers can be done if you're smart enough and go at it. Atomic physics is the real challenge, and that's a great need going forward. Cloudy itself is in good hands. I've had about 20 students over the years. These 4 have stuck with it. So Cloudy has a bright future, and they're all in good places and continue to help out with the code. So just to end this very, very quickly, that the same image, a human being looking up at the sky, what's going on out there, if you're just looking at the BPT diagram, okay, we're done. But if you want to really get into the spectrum, if you want to get down and dirty and try to figure out all the things the spectrum is telling you, you're going to get very quickly to the frontier. And you'll want an atomic physicist somewhere near you. Okay, well, thank you very much.